we can get started. So, hi everyone, this is the second last CSP seminar of this semester. We still have one tomorrow. So today is our great pleasure to have Lijun Ding here. So we soon will be assistant professor at Tamu IOE. So I know him quite a long time since he's PhD student at Cornell, and then now he's a postdoc at UW Medicine, and joined with UW Washington with Marion Frizzell and Stephen Wright. So he's doing some very interesting work in low rank matrix recovery. So let's welcome. For the room is yours.
Thank you, Tim. Thanks for the introduction. I'm currently a postdoc at medicine. So today I'm actually going to talk about work that I was doing during my postdoc time at University of Washington. So you can see all my collaborators are from University of Washington. So this is a work done during that time. And the title of the talk is, I hope you can still see it, from the not being hidden by all the pictures, but it is really flat minima generalized for low rank matrix recovery. So I only have 17 slides, so please ask questions. I have given this talk many times, so should be able to answer most of the questions. And I hope this is an interesting and enjoyable experience for you. So, so the motivation of this work is really that today's machine learning models are usually heavily overparameterized. So we are really considering this supervised learning setting, where we have xi as the input features of the data, and yi is the output or the labels. And we are using some hypothesis class parameterized by this theta parameter, and we are using certain laws measuring the prediction and the actual label. So here we are using empirical minimization loss approach. And we are trying to minimize this loss over this parameter theta. So this work is really motivated by today's machine learning models, which are heavily overparameterized. In the sense, the dimension d of this parameter theta is much larger than the sample size n here. So I do have more samples than I do have more parameters than the samples I have. So overparameterized models induce a lot of interest. I'm not sure 2018, maybe 5 years ago, is not that recent, but this was a phenomenon called double descent, and this was motivated by these overparameterized models. Even early reference was showing that these overparameterized models, which is carried over D here, and you can see the ratio is much larger than 1, sort of indicating the case that this much bigger is indeed true here. And those overparameterized models have good training accuracy as well as good testing accuracy. Of course, it doesn't mean it can do all the magic. So if we use some random fitting labels, meaning that this yi really does not correspond to the actual label, but some kind of random, then because this is really 10 classes, in the training data, it can still perform 100% accuracy, but because there are 10 classes, it's then if I sort of randomly shuffle the label for if there are 10 classes, then the randomness of the correctness, the probability of making a red guess over 10 classes is 10%. So this is trying to show you these models have a very expressive power and can feed the data perfectly, feed the training data perfectly. Of course, the caveat here is that overparameterization is not the cure for everything. It's not the panacea for everything. So once we overparameterize, there is a continuum of many solutions that can achieve zero loss. And it won't be the case that all of them are generalizable. So the question we ask here is like, why do some solutions generalize while others do not? So in this talk, we will revisit a kind of old idea, or maybe classical idea, if you call. So it was sort of proposed in the 1970s by Hiracher, and it got revisited in 2016 by Short-Ari. So the idea here is that suppose this is actually my training loss. And what I mean by this flat landscape of the loss correlates with generalization. So let me first give you an intuitive explanation of what I mean by flat minimizer. So basically, these are the minimizer or the local minimizers that whose function grows slowly around its point. Well, the sharp minimizers are those points that the function grows much faster. So this is really a relative concept, right? So this one have a function growth that is much faster, while this one is much slower. And the hypothesis is that those flat ones, when we think about their testing error or their generalization ability, they have a better chance to be more generalizable. So it induced a lot of recent interest. I want to move now. So it induced a lot of recent interest in terms of the algorithmic aspects. So people developed a lot of algorithm based on this idea, sort of trying to find these flat minimizers. So I list the example here, and actually from one talk that given by I think by Meta, one of the researchers, like who is very good at like pitching, like in getting, I think getting startup monies. Like he said like this sharpness aware minimization is actually being used in practice, and this is like sort of one of the key for the success of deep learning models.
Yes, actually, one of the authors, Hessian, gave a talk.
Yeah.
Weeks ago.
Yeah. So this is something like really happening, not something I made up. Okay. So the actual question that we will study is that do flat minimizers generalize for a broad family of overparameterized models or problems? And so we won't actually answer the question whether some solutions do not generalize. We will only answer the questions whether flat minimizers generalize or not. And the class we will focus on today is low-rank matrix recovery problems. So even within this problem class, there are like many problems here I listed here. This is a problem that I have been looking at for maybe 80 years now, so I'm kind of very familiar with it. And this is kind of the reason, one of the motivation like why we study this problem. Of course, we will give more formal explanation later. And in this class, we will see that flat minima, okay, we are trying to recover some kind of a low rank matrix here. So in this problem class, we will see the flat minima exactly equal to the ground truth under standard statistical assumptions. So this is a much stronger statement than than the usual understanding of generalization, because I have exact recovery, or you can still say they actually generalize. So the main message I want to convey to you in this talk is that within this problem class, the flat minimizers indeed have the generalization power. So I think it's a good point. If you have any questions, you can ask.
So here the generalization means that the matrix completion, your training error is on the observation, generalization is on the thing.
Yeah, you can be thinking that way. And basically, you're taking the expectation and of the random distribution over the observations. Yeah. Okay, so let me let me make this problem more precise. So we are getting into the mathematical model and trying to make everything precise, not just words. So in this setting, there is some underlying ground truth matrix M sharp that is unknown to us, but we are trying to recover it. And we're trying to recover it from the data, this B and this A map, which formally should be really written when there's a dummy variable X or any variable X of size D times D. It's the trace A1 applied to X, the inner product of A1 and X, and all the way up to AM over X. So this M should really be considered as the N in the previous slides. So the things that are known to us is this A, this linear map, and this B, this vector. So this B vector is of M dimensional, where this A map is a linear map from D times D matrices to M dimensional vector space. And we know this B and A, we are trying to recover this M sharp. We will assume that this rank of the M sharp matrix is much less than D, then reflecting the name of, okay, I didn't have the low rank here, but this is really reflecting the name of low rankness. Actually, any questions on the setting? This is very important. Okay, I hope it's all clear to you. So the loss that we will consider here is the L2 norms.
Assume that A has RP conditions, or
it's like, okay, so in the we will see later what kind of assumption we need. But here, just consider A as some matrices that we know, or some measurement matrices we know. So the loss we will consider here is the L2 loss square, or the L2 loss usually referred to. And we're trying to, instead of using one matrices to parameterize this M sharp, we will use two factors, L and R, of size D times K. So in this problem, I have two factors, L and R, and I'm applying this linear map to this product and see whether it matches the actual observation B. So I'm trying to minimize the mismatch between the predicted label and the actual label. And the measure of loss is the L2 norm squared. So overparameterization in this context, note that I use two factors of size D times K. So I will use the K that can be larger than the rank, the actual rank, or the rank of the ground truth or the signal M sharp matrix. So I use more parameters than needed, in the sense that if you have an M sharp matrix of rank R sharp, if you consider the SVD of it, the singular value decomposition, you only need to use about R sharp times D that many numbers to represent it, or floating points numbers to represent it. But here I use this K, which is the size, number of columns of L and R. I use this K to be much larger than the R sharp. In the sense, this can be overparameterized. Or you can also think in the way that this D times K can be much larger than the sample size M. Like I have no control except this K has to be larger than R sharp. So the number of parameters in this case can be much larger than the sample size. There's no restriction except this K has to be larger than R sharp. So the reason of studying this work, studying this problem class, is it shares some characteristics as deep learning models, such as homogeneity as the feed-forward neural network. And it is really a prototype for non-convex problems. Yeah, it has been studied for years now, maybe 2 decades, if you know the history. So there are like sort of the reasons, formal reasons in studying this model, trying to understand the
homogeneity is a feed-forward network.
Basically
nonlinear network, like homogeneous nonlinear network or something like this.
What did I? Oh yeah, what I mean is you using some ReLU activation.
Oh, okay, and then one layer have this kind of homogeneity, like you have a constant instead of
Yeah. So if you multiply each weight matrix by alpha, then you can pull the alpha out. You can pull the alpha out, like alpha up and alpha squared.
How about you have like multiple layer?
Yeah. So so in this case, it's homogeneous of degree 2, I think. But yeah, the more layers, the more. I think for L layers, it will be homogeneous of degree L. Yeah.
So what's the common shared characteristics between?
Oh, I'm just saying like they are all homogeneous, like, in that sense. So to further, okay, let me now try to define the flatness measure. So for this problem, because I do have this M sharp, if you remember, do generate this V. So the optimal value of this function is really 0 if my K is larger than R sharp. Okay, recall your basic linear algebra. So the solution set would be all these L and R whose product matches the vector B after linear map A. So this would be the solution set. And the reason of that is because my M sharp is rank R sharp, and I use K larger than the actual rank. And because I use K that can be much larger than R sharp, there could be many solutions or many L and R such that they do belong to this class, do belong to this set, or they do satisfy this equation, but they are not equal to this M sharp. Because in the sense that I have more parameters than the number of equations here, because I have no control on this K. So now let me now define the. If you recall what I said earlier about flatness, are those solutions that have function growth much slower, slow. And if you recall, those are local minimizers or minimizers. Then for minimizers, the first order information or the gradient is 0. So the function growth is mainly captured by the second order derivative or the Hessian. Okay, so for local minimizers, the function growth is mainly captured by the Hessian because the first order information is 0 or the gradient is 0. So in other words, so this is trying to reflect what I have said. If you sort of add U and V to the two factors, then this is almost equals to this Hessian applied to the UV direction, or half of the Hessian applied to the UV direction, because my function value at L and R is 0. It satisfies this equation, right? And my first order information is also 0 because it is a local minimizer or global minimizer actually. So the main gradients of the function growth is captured by this Hessian.
This is a directional Hessian, so if you choose your U and V to
just any U and V.
But I think eventually, if you want to measure the flatness, do you need to which specific direction?
So in the end, I will average.
Okay.
So in the end, I will average all the choices of this U and V, meaning that I'm taking. Okay, so you think of this. Think of this. This is the Hessian as some kind of a large matrix, and it is of square shape. It is a Hessian, right? So then you're taking the trace of it. And this can be as an average measure of the growth, or if you want to sort of average over all the directions, this would be the notion that one want to use. So in a sense, we sort of reduce the function growth, which could be Hessian is like a high dimensional thing, trying to reduce to a single index thing. Then we're taking the trace here. Okay, let me now define what I mean by flat solution, or you should really think of this as flattest solution. So we are like, okay, so this L and R, we are thinking about all the solutions of the original, the L2 norm square problem or the L2 loss problem. So we are selecting over all these L and R that belonging to that solution set. And we are choosing the one that has the smallest trace of Hessian. So we are picking the one has the smallest flat measure. So this is what I mean by flat solution rigorously or mathematically. Any questions on the definition? So, okay.
On the previous slide, can you explain what the notation means when you have UNV in brackets next to the Hessian? Does that mean like U transpose times Hessian times V?
No. It really means okay. So I use some okay. So you think of this as you should really think of this U and V. If in this notation, it would be like U in the top, V on the below. So basically, I'm stacking my variables as L and R as two things. So this is actually my variable, and U and V means like U. Okay, so the question we want to ask now, making very precise, is whether this product equals to M sharp. We want to understand whether the flattest solution or flat solution does it recover the M sharp. If you have been working on low rank matrix recovery for a while, then you will know that the classical approach, or sort of gold standard here, or golden standard, is using the nuclear norm. So you find the X that match the observation of the linear map A, and this X has to be smallest in terms of the nuclear norm as a surrogate of the rank function. You can consider our flatness measure as a different complex measure, but flatness is in some sense more intrinsic because I didn't use extra knowledge like in capturing this problem, and sort of the nuclear norm is like some kind of external. It's sort of knowing the information of the rank being small. So the plot here is trying to do an empirical study. So on the right is the nuclear norm minimization. On the x-axis is the number of samples. On the y-axis is the number of, sorry. So on the axis is the dimension. So this is dimension from small to large. And on the y-axis is the number of samples from small to large. And white indicates successful recovery, while black indicates failure of recovery. So white here means that I indeed recover the M sharp matrix, while the black here indicates I did not recover. This is like the nuclear norm minimization approach. So the classical approach here. Well, on the left is some kind of convex relaxation, but you don't need to know that detail at this time. Just thinking of this as the minimizer of this problem. So think of this as the flat solution minimizers. As you can see, if you cannot see, in some sense, these two plots are very similar. In a sense, if I don't tell you that which one is nuclear norm minimization, you may not be able to tell like which one comes from the nuclear norm minimization. Okay, so the message here is like it looks like the flat solution has the same power in recovering the M sharp matrix as the classical approach, so that you cannot differentiate it too. So I'm considering a particular case called matrix sensing. We will specify later.
So this convex relaxation, the solution is unique for this convex relaxation, right?
Yeah, so in the regime that we can prove it is unique. But of course, in practice that we use some solvers to find it. And I didn't specify what solver we use. Okay, let us consider a very simple setting. I think it's quite instructive. So in the simple case, which I think some of the groups really like to study, actually, there are people doing this just for this problem. Like you can publish paper just by studying this function sometimes. which is x, y. Okay, x is a scalar, y is a scalar, and minus 1 squared. Okay, so this is like the extreme simplified setting of my previous low rank matrix recovery problem. When the okay, even simpler than this matrix factorization, where I already set A to be the identity. Okay, so we are thinking a very simple case, xy minus 1, taking the top power to the square. So in this very simple setting, okay, there's actually no issue with, it is not over-parameterized, it's just exact parameterized, but it does shed light on some of the notions that I have explained earlier. So these curves here are all the global optimizers, and okay, to give you like a physical visualization of what the function looks like. And for the flat solutions, you can, okay, so this 1, 1 or this minus 1, minus 1 are not only just global minimizers, but they are actually, if you verify the definition of the flat solution, they are also the flat solution or the flattest solution, and they are also like non-minimal, because if you think about this curve, which is x1 equals to 1, and if you compute x squared plus y squared, like, okay, basic inequality or things you learned in your high school tells you like this point is in a sense like non-minimal, and y equals to 1, so it is actually balanced. So this shows that flatness has something to do with the regularization concept that in the past. So, and at least in this particular example, we see that in this particular example that this xy minus 1 to the power square, flatness and non-minimal and balanced are exactly the same. Yeah, just here, this 1-1 solution is both flat, non-minimal, and balanced. You can prove this in a more challenging setting where this A is just the identity map, and we're actually doing, we're actually dealing with matrices. So for this above problem, where the A is identity, where I have LR transpose minus M sharp to the power square measured by the Frobenius norm, one can show that this flatness measure is exactly the same as the non-minimality, meaning that it solves these like optimal this objective function where it is sum of the square of the Frobenius norm subject to the L times R transpose equal to M sharp, as well as being like balanced. So if L and R is within the solution set, then if it is exactly balanced in this sense, then it is also flat and non-minimal. So these three notions in this context are exactly the same. So this gives you some sense like why flat minimizers can work, because this flat measure is kind of very close. At least in this setting, it is exactly the non-minimal or the minimal norm sense. And if you further know that the non-minimal in this sense actually just means the nuclear norm. So it does some kind of actually is mimicking the nuclear norm minimization. And then there's no surprise why it can work in practice. Okay, so this is trying to give you some why we care about non-minimality and balancedness. So both concepts are kind of important for both regularization, for both like a generalization perspective through regularization, as well as like computational perspective. So for the, do I have it here? Okay, okay. So let me stop saying that. So as a lemma from, okay, as a linear algebra fact, thinking this way, the sum of square is actually equal to the nuclear norm. So there should be not much surprise that flat solution, if it is non-minimal, then the product is also minimal in nuclear norm. So I want to say that if the flat measure is almost the nuclear norm, then there is not much surprise that one can sort of recover the ground truth or the M sharp. But of course, this is not enough, because this is a very particular case where the A is just the identity. Yeah, any questions up to now? Okay, great. So let me now kick in, try to explain the
Go back to,
yeah.
so you are saying balancedness, so this all three conditions, they are included.
Yeah. In this particular setting where the A is the identity.
So which means that if you're starting from a small initialization and you convert the solution, and then there should be a flat.
In a sense, if okay. So okay, so if it converges to a flat solution, it is automatically non-minimal. Or if you can show the convergence limit is already non-minimal, then it's already flat. But whether the limit is flat or not, or whether it is non-minimal or it is balanced in this sense is another question. And I can tell you actually, if you run gradient descent with small but not exactly zero, then they are not exactly balanced in sense. Now let me give you some more rigorous mathematical ways, like in showing why the strategy or how to show the flat minimizers are exactly the ground truths or the M sharp. So this is our definition. We are trying to minimize the flatness measure subject to this L and R are in the solution space, which basically means the product equals to the observation B or the vector B after linear map A. The main lemma here, which this is actually the lemma that is sort of being the core of the paper. So flattest L and R correspond to minimizers or the product of LR transpose of the following problem. So here you see the presence of the nuclear norm, but we have two extra scaling matrices or rescaling matrices D1 and D2. They are defined by the data. Recall my linear map A has some AI matrices. So they are defined by those AI matrices, this D1 and D2. Subject to the constraints, of course, I still have this equality constraint here. But remember, my L and R is of size K. So this corresponds to these rank constraints here. Two factors of size no more than K, then the product can have rank no more than K. So this is where this constraint here, so rank is here. So if you think about this, if your K is as large as D, then this one already disappear. Like D times D matrix cannot have rank no more than D. So the way that convex relaxation that I mentioned earlier is that we simply drop these rank constraints. So we no longer have these rank constraints, and we only consider our previous this objective with these linear constraints, AX equal to B. Yeah, any questions? So our strategy is then like trying to, so we want to show the flattest solution, they recover the M sharp. And our strategy is trying to show this convex relaxation at Miss M sharp as the unique solution. So this will be our strategy, like in terms of the proof. So if we can show that M sharp is the only solution to this convex relaxation, then M sharp is also the or unique solution to our previous definition of the flat minimize. Of course, the difficulty here is that I have data here, but I also have the data in the objective. Because this D1 and D2 comes from this linear map A, which we consider as a data, something that we know. And if you recall the nuclear norm minimization, there is no D1 and D2. So at least the objective does not involve the data. So that actually makes the analysis a bit easier. So So I won't explain the actual proof, but I want to show you some results for two problem classes I have mentioned earlier. One is this matrix and bilinear sensing, and the other is one hidden layer neural network. And but with the quadratic activation, so it is actually the same as the so-called covariance matrix estimation. And the similar results holds for other settings I have mentioned earlier, such as matrix completion, robust principal component analysis. So here, okay, good. So here we have these AI matrices, and Qing asked whether we assume some RIP. Yes. So in the Gaussian example case, basically we're assuming some kind of RIP. So we're in the Gaussian example means that this AI are IID standard Gaussians. So each entry of each matrix is the standard Gaussian, and they are independent of anything else. We also consider the Gaussian bilinear ensemble, meaning that these AIs are rank-round product of UI, BI, where UI and BI are d-dimensional Gaussian vectors. So our results, our theorem, is that in these two settings, with once the sample size, I really should use n here, m is larger than r sharp times d, thinking of this as the least number in representing a R sharp matrix. Then with overwhelming probability, any flat solution, L and R, their product is exactly equal to the M sharp. So this really utilized some previous knowledge on this RIP. And moreover, as I mentioned earlier, I care about something called non-minimality and balancedness. We can show that those flat solutions, when we measure them according to the sum of square of the probability norm, it is only like a slightly larger than the actual nuclear norm of the M sharp. And and you can show this one is actually the minimal norm solution. So the flat, so in these sort of for like in general, this A map, like when A is not identity, then the flatness is very close to the non-minimal solution. But as we verify numerically, they are not exactly the non-minimal solution. They are also approximately balanced, but they are not exactly balanced. So we do run some experiments to tracking whether this equality holds, and they actually differ by a significant, a noticeable amount. So you can, it's not like 10 to the minus 11 or 10 to the minus 6. So it's something like 10 to the minus 1 to 10 to the minus 2 or 2 to 3. So there's a noticeable difference, meaning that they are almost balanced, but not exactly. And if you sort of consider whether this sample size is like as minimal as possible, you can show this matches the guarantee for nuclear norm minimization. And in some sense, this is information theoretically most possible. In the sense, the least number of samples you need to recover abstract. Yes.
If you can find the solution LR triangle that's equal to M sharp, is it necessarily also a flat solution? Like, does it also go the other way?
Sorry, can you repeat?
So like here you're saying that any flat solution must have that it's equal to M sharp.
Yeah.
You can find the solution LR transpose equal to M sharp. Is it necessarily flat?
Yeah. So the short answer is not, because there is ambiguity. You can always apply some invertible matrix, right? Yeah. So, and if you don't think about invertibility matrix, you just some scalar, so that I won't make wrong about the transpose. And there is a scalar difference. So, and you can show that if you use like this scaling, the Hessian will increase, but or the flatness will increase. So the solution suddenly becomes kind of sharp there, but it does not really change their product. Okay, next I will hopefully maybe explain using 3 minutes explain the setting, but maybe 30 seconds to explain the result. So this is a single hidden linear network, but with quadratic activation. So let me now use the mod here. Suppose we have in this case we have some actual data x that is d-dimensional, and we will assume later x is Gaussian, and response vector, so sort of a prediction made by the linear network, is given by the function. So my x going through this hidden layer, which I think there is some teacher network parameterized by this U sharp, and going through some kind of activation Q, and then in the end I do a linear prediction using this V, or weighted by this V. So here this U sharp is of size D times R sharp. So I need, yeah, D times R sharp, and V. So and V is some R sharp dimensional vector with some positive values, R1 many positive entries, and R2 many negative entries. And Q, this activation function, is the square function where I will apply it entry wisely to the vector U sharp transpose Y X. So I will apply the Q, the quadratic function, to this hidden the prediction after one hidden layer entry wisely. Of course, this is like the teacher network, which we do not know. And the prediction Y hat is using another we call student network. Here this U, okay, so here this U is this little U, okay, this little U here with one K1 meaning ones and K2 meaning negative ones. And I'm doing some over-parameterization, so K1 will be larger than the number of actual positive ones, and K2 would be larger than the number of negative ones. And my U would be just D times K. There's actually no, yeah, I should really give the size of this U, but this U will be of size D times this K1 plus K2, because I need the dimension to match. So this U would all be of size D times K1 plus K2. Then if I use the L2 norm, it will be the prediction with this parameter U and the data xi, and yi is my actual label or output. Actual label, let's try this. And my U is of size D times K1 plus K2. Because this K1 and K2 is larger than R sharp there. So this is the setting where we doing some over-parameterization. And flatness in this concept is again just the trace of the Hessian. Oh, okay. Even though I have only one variable, I can still compute trace of Hessian. There is a Hessian and I compute the trace of it. And I will minimize over all the U such that they perfectly match the data. Yeah, there's a lot of going on here. Can you, any questions?
It's a quadratic activation.
Yeah. I'm not saying it's, yeah, you're right. Yeah, actually, so the key of like sort of what we found about like this problem, okay, this problem is not It's not proposed as proposed by us. It's proposed by someone else. So this problem can actually be reduction to more understandable objects. So this function here is really the same as this U. If you partition into this U1 and U2, you can see this U is actually the same as it can be rewritten as our previous matrix factorization problem, where this U1 is of size D times K1, and this U2 is of size D times K2. So the first K1 columns correspond to this U1, and the rest of K2 columns correspond to this U2. Okay, this is after some linear algebra. And the AIs will be of this shape, XI transpose. And this M sharp matrix would be of the form that are previously the U sharp I mentioned. Then you multiply the diagonal of B in the middle, and then you multiply the U sharp in the end. So M sharp here is a general symmetric matrix. So this problem would reduce the phase retrieval and covariance estimation if there is no like a U2 part or there is no negative part. If you know what the phase retrieval and the covariance estimation. So our result, so we did not really study this problem, but we studied the equivalent problem, and this is exactly the same as previous one. So using the sort of the technique from low rank matrix recovery, we can still show that if you have a new sample X that follow this Gaussian distribution, so assuming all these Xi's are Gaussians, once the sample size is larger than the R sharp times B, then with high probability, any flat solution UF, so defined in here, defined here, where I minimize the trace of the Hessian subject to the U in the solution set. Then the prediction error is exactly 0, like the best you can hope for, because I have no noise in this case. Or the testing error, if you use. Okay, good. Actually, that's the end of talk. So I'm not sure if you have more questions, but welcome to ask.
Can you go back to previous slide? So we don't know M sharp in the level, right?
In where?
So F U1 F of U1 and U2.
Yeah. We do not know this one. We do not know M sharp.
Okay.
But we know the A applies to this M sharp.
I mean, I may have missed something, but in this, shouldn't you have some dependence on your over-parameterization, like on K?
Yeah. So yeah, this was not okay. So the assumption was here, this K1, the number of positive ones is larger than the positive entries in this B, the actual parameter. And this K2 has to be larger than the number of negative entries in this B. So you should really consider K equals to K1 plus K2 and have these particular assumptions on this number of positive and negatives.
So a question. So here you are seeing that you are finding the flattest solution, and then this generalization will be good.
Yeah.
But In practice, we are in a setting, I mean, we quantify the relationship. I mean, so we're not achieving the most flat solutions. How does it?
Yeah, that's a good point. Yeah, so
generation error or something.
Yeah, so basically in this setting, it is not hard to relate the generalization error with the let me maybe go back here. Okay, so it is actually not too hard. So it is actually not too hard. So suppose my my flatness measure is like very close to optimal value, but not exactly. So I have some gap there. So some difference. The gap is measured by the difference. So this value minus the optimal value. And also I may not, match the optimality. So there will be some error measured by this prediction minus this b. So the difference here. So so it is not hard to show that the sort of the L and R, the difference between L and R, the product between the product of L and R to M sharp. Okay, maybe this way. So it's not hard to show something like showing some kind of inequality, like my guess would be 3. Something like the trace of the Hessian of L and R, like minus maybe the optimal value. So I write this LF as the flatness, the flattest solution. So this would be the gap of the flat measure. Gap. And plus like the number of the magnitude, maybe 9, of this A times L and R transpose minus B measured by the LT. So kind of if you have some approximation in terms of these two quantities, it's possible still to the recovery error gap. Yeah, it's possible. But
is it tight or
in a sense, this is like some kind of the best one can hope for. It's already in a sense most dimension independent. Like okay, let me put it this way. I think this error bound is already dimension independent, so this is the best one can hope for. Okay. Yeah, but if you consider more local measures, like some kind of PKT violation in this problem, then it will be very challenging.
You mentioned convex relaxation. So the second line is the original formulation.
This here?
No, the line before that is
this one. Yeah, this is the original formulation.
The one in the lemma is the convex relaxation.
This one is equivalent.
Equivalent.
In the sense that if you find this X, you can directly recover the solution of that, and the reverse way is also true. So if you have a optimal solution for this problem, the upper problem, then you can directly construct the minimizer of the things in the lemma, the optimal solution in the lemma. But the reverse way is also true, in the sense if I have optimal solution of this of the problem in the lemma, then I can construct the optimal solution of this upper problem.
I see.
So they are equivalent in an optimization sense. So there is no statistical assumption here.
Okay.
And I guess the nuclear norm comes from the trace because you are summing up all the eigenvalues and
summing up, summing up all the diagonal values of the Hessian.
Hessian. Yeah.
So in this case, depending on maybe 5 lines of algebra, you can figure out this one can be sort of relates to this one. Not obvious.
And so what is the convex relaxation again? I forgot. So that's one.
Basically, you drop the rank constraints.
Okay.
So maybe with a limitation of
Great.
time, that's a second condition of the great comment.